All right, we're now going to introduce what we call ionization energies. Ionization energies are energies, the energy required to make an atom an ion. All right, now I say it that way because that'll help you remember what an ionization energy is. Unfortunately, they don't call it cationization energy. They should have called it cationization energy because ionization energies are always associated with the removal of an electron from an atom, as shown here. So here's X. Take X and make it a positive charge by removing an electron. The energy associated with that process is the ionization energy. Good. Now, look at this. See how as you trend towards the right within your subshells, the energy necessary to remove an electron increases. All right? So these are ionization energies. Ionization energies are always positive, or it always requires energy to remove an electron from an atom. And you can think of this as a family. The model of a family works for this as well. If you say, okay, so there's parents, couple parents, that's the nucleus, and there's a lot of kids. Does it matter if somebody takes away one of the kids? Yes, that's going to be hard. That's going to require a lot of energy. So no atom wants to give up kids. It requires energy to remove an electron. But it requires a different amount of energy to remove an electron from different atoms. So for example, lithium, it's not terribly bothered by losing an electron because then it has the electron configuration of a noble gas, right? Magnesium, same thing. If it loses an electron, it's closer to a noble gas, so it doesn't require as much energy. It still requires energy, but not as much. On the other hand, if you look at fluorine and chlorine and bromine, these require a lot of energy to remove an electron because they don't want to lose an electron. What would they prefer to do? They would prefer to get an electron. That's right, because then they would have a noble gas electron configuration. Okay? Now, there are interesting trends. See this trend? Boron, carbon, nitrogen, oxygen, fluorine, neon. There's an interesting trend there that with our Bohr's model of an atom, just our orbital model, it wouldn't be able to be explainable. But we have the ability to explain these irregularities using our orbital diagrams, following our new elemental or atom model of the atom. Here are our ionization energies for lithium, beryllium, barium, carbon, nitrogen, oxygen, fluorine, and neon. And here are our explanations down here. See, we see for this orbital diagram, this is what nitrogen looks like. And if you remove an electron from nitrogen, it's hard because it's taking one electron away from a half-filled subshell. And when you have a half-filled subshell, you have a degree of stability. You get a degree of stability when you have a full subshell and a little bit of stability when you have a half-full subshell. So removing an electron from nitrogen here requires a little bit of energy. However, a little bit more than a typical than its neighboring atoms, carbon and oxygen. Removing an electron from oxygen results in a half-filled subshell, and so it doesn't require as much energy. So that's why oxygen is lower than nitrogen, and why you see this bump, right? Same thing with this bump on beryllium. Okay. Successive ionization energies. You can remove more than one electron from atoms, but it requires more and more energy to remove those electrons. So looking at lithium, the first atom or first electron to be removed requires this much energy. The second, a lot more. The third is twice as much as the second, but wow, look at the jump between the first and the second. For boron, the first three require a lot of energy and increase, but look at the jump between the third to the fourth. So what do you think? Why are we seeing this specific jump from, in the case of fluorine, 7th to the 8th electron? Oh, I think I know. You do? How do you know? Well, because fluorine, I remember in my high school chemistry, fluorine has 7 valence electrons. Do you have the periodic table? Yeah, let's bring up the periodic table. Here's fluorine.
Yeah, it has 7, so it's in the 7th column, so it has 7 valence electrons. So it requires energy, but those are valence electrons, so they're easier to remove. But if you remove something from the noble gas core, that requires a lot of energy.
That's right. Very good. So lithium has 1 valence electron, requires energy to remove it, but if you begin to remove electrons that are in the noble gas core of lithium, or in any atom for that matter, then it requires much more energy. Good. The opposite of ionization energy is called electron affinity, and it's the energy associated with giving an electron to an atom. All right. So what did I say about ionization energy? Does it require energy or release energy when you remove an electron from an atom?
You said it always requires energy to take a kid from a family. I mean an electron from a nucleus.
That's right, from an atom, right? Electron from an atom. It always requires energy.
Yeah.
Okay, but electron affinity is where you're giving an electron to a family, or giving a child to a family, or electron to an atom. What do you think? You think that'll release energy or require energy? If somebody comes to a family and says, here, I have 1 extra kid for you, are they going to say, no, I don't want that kid? Or are they going to say, oh, yeah, we'll take 1 extra kid?
Well, I feel like they'd say, yeah, they'd take it, but I don't know if that's right.
Well, it is right. Every atom will actually release energy upon the addition of 1 electron. So that's interesting. Every atom will release energy, -141 in the case of oxygen, to receive an electron. Not so for the second electron. The second electron always requires energy, but every atom will always take 1 electron and release energy. So let's go back here to our ionization energies. To remove an electron, it always requires energy. So these are all positive values. But electron affinities, they're all negative values. The first one is always a negative value. And it increases, becomes more negative, more energy released as you head to the top and to the right. And this is because if you look at our periodic table, giving an electron to fluorine, that gives us a noble gas electron configuration. So you stabilize it a lot. Giving 1 electron to carbon, it gets it closer, but it doesn't stabilize it as much. Giving an electron to cesium requires some energy, releases some energy, but it already has so many kids, it can barely tell the difference. Giving an electron to lithium, that releases a lot of energy because it will give needed electron density to that nucleus. Okay, very good. Excellent job. Done with chapter 8.